Hello and welcome to one of the first regular sessions of this year's Eurocrypt on code-based cryptography. We have three, sorry, I need to mute this. We have three talks scheduled in this session. Just one logistic reminder in the beginning, if you have questions after the talk, please approach the microphone in the front so that the online participants can also hear your questions. So can we bring up the slides for the first speaker? Okay, perfect. So yeah, it's a pleasure to announce the first talk of the session on algorithms for matrix code and alternating trilinear form equivalences via new isomorphism invariance. And the talk will be given by Anand Kumar Narayanan. Please.
Thank you for the kind introduction. Can you hear me? Awesome. So good morning. And I'm Anand from Sandbox AQ, and I would like to talk about work with Yuming and Gang, both of whom are in Sydney, on algorithms for trilinear form isomorphisms. But let's begin with by staring at something very familiar. So if I were to give you two square matrices, phi and psi, and ask you if there is another matrix A that takes one to the other by transposition, can you tell me the answer? Yes, right, because this is a familiar notion of similarity up to basis change, and we can answer immediately. So you take phi, you compute its Frobenius normal form, or if it's over the complex number, Jordan canonical form, and you do the same for psi, and if you see if they are the same, and the answer is yes, otherwise no. So it's rather simple. But what if I gave you two tensors and asked you if there is some kind of a basis change on each of the dimensions that takes one to the other? This small step in dimension, going from 2 dimensions of square matrices to tensors, which to us is essentially just a cube of numbers, is a huge leap in computational complexity. And it turns out that most of the linear algebraic problems that we take for granted as easy in 2 dimensions, they turn out to be hard in 3 or higher dimensions. And it's curious because it's sort of like going from 2-sat to 3-sat, but a lot of these problems also have an average case complexity, which is amenable to cryptography. So in particular, we will be looking at a family of tensor isomorphism problems over finite fields. And it's a close-knit complexity class of problems, some of which are familiar to cryptographers. For instance, many of Pateran's original multivariate cryptography falls in here. Also, there's a long-standing problem on p-group isomorphisms, but I'll concentrate more on 2 tensor isomorphism problems that were the stronghold of 2 new NIST submissions for post-quantum signatures, namely MEDS and ALTEC. In summary, I'll present 2 new algorithms for finding isomorphisms of tensors, and they're going to be polynomially faster than all previous known algorithms. And in terms of consequences, asymptotically, the bit security of MEDS is roughly cut in half. And for ALTEC, there's no need to change any parameters because all of us were part of the ALTEC team, and we started this endeavor trying to understand how hard these problems are. Okay, so the novelty is going to be some kind of an invariant. It's much more complicated than Frobenius normal forms, but sadly much less discerning. So we'll only get exponential time algorithms, or sub-exponential, depending on how you see it. Okay, so on to the fun stuff. So to us, a tensor will just mean a cube of numbers, and these numbers are going to be from the finite field FQ. Okay, and to us, to a tensor, we can associate a trilinear form. A trilinear form is nothing but a function that takes 3 vectors and maps it to an element. And it's not hard to see how to go from a tensor to a trilinear form. You just write down the 3 vectors, which are the inputs. So when I take an inner product with this tensor, I squeeze it, and I get a matrix. Then I take this matrix and take the inner product with this vector. I get a vector. And I take this vector and take an inner product here, and I get an element. So it's that simple, and it's not hard to see that the correspondence also goes the other way. And we will also be interested in tensors with a more rigid symmetry. And these are tensors wherein if I were to take 2 inputs that are the same, the answer is going to be 0. Okay, so these are generalizations of skew-symmetric matrices, essentially. Okay? Okay, so what's an isomorphism? We will look at two kinds of isomorphisms. The first one underlies MEDS. So here, a triple of invertible matrices acts on a tensor, and it maps it to another tensor. So this new tensor is going to be denoted by phi ABC. And how is it defined? So all you do is you take the three inputs, and you multiply the three inputs on the left by the corresponding matrices in each dimension, A, B, and C, and then you apply the tensor phi. Right? And this is a perfectly good trilinear form because everything is linear. And so two tensors are said to be isomorphic if there exists a basis change that takes one to the other. So in terms of these pictures, the way to think about it is that if there's an input that comes in, it goes through this matrix, and then it goes to the tensor. That's it. OK? And the second action is the one that's behind Altec. And here, we restrict to these alternating tensors, so these have more symmetry. And further, not three, but just a single matrix acts. And the action is very similar. So in each dimension, you multiply by the same matrix. So it's essentially the same. But the changes are subtle because of the symmetry. The input is just a two cubes of numbers, right? But in the alternating case, there is redundancy, so you only need to transmit a third of the numbers. So one point I forgot to make is that the moment you have a notion of isomorphism, you can invoke Goldreich, Picali, and Wigderson, and you get a sigma protocol for zero knowledge, and then you do Fiat-Shamir, and you get a signature scheme. Right? In those signature schemes, when we use alternating trilinear forms, the public keys are a third of the size, if I take the same size tensors. And also, I don't have to transmit three matrices, just one. So the signatures and the secret key are also slightly smaller. OK, so this is just a setting. And so here's our preparation for our algorithm. So I told you that I'm going to try to get an invariant. So in the Frobenius normal form, so you have a matrix, and it maps to some number. Right? So we don't quite know how to do that. So instead, our invariant is going to have a tensor and another input. And this extra input is just going to be some vector. We're going to call these co-rank 1 projective vectors. But it's just some vector up to a scalar multiple. I'll tell you what it is in a moment. OK? And it's going to map to some object, which is called bracket phi u. So I haven't told you what bracket phi u is, and I haven't even told you what kind of object it is. But I'm going to think wistfully, and this is the sort of invariance that I want. So if I take the bracket of phi and u, that should be the same as taking the bracket of phi acted upon by ABC, just some triple of matrices, and u acted upon by the inverse of the matrix acting in the first dimension. Right? So I want something like this to happen. So I'm going to construct such an invariant. OK, so I have to tell you what co-rank 1 point is. So I have my tensor. I take a vector. And if I do an inner product, I'm going to get a matrix. So typically, it's going to be a matrix of full rank. I don't like those. And I want the matrix to have rank exactly one fewer than n, which is n minus 1. And I call those points as co-rank 1 points. And for my construction, I have to really projectivize. So I mod out by scalars. And wherever you see a hat, it's just projective. But I will keep calling them u. It's not a big deal. OK. So what is it good for? So I'm going to start with a random co-rank 1 point, u. And I'm actually going to call it u1 because I'm going to iterate. So what I'll do is I'll start with a tensor and u1. And by design, u1 is co-rank 1, right? So if I look at the inner product between the tensor and the vector, I get a matrix. And it has a right kernel of dimension exactly 1. Right? So up to scalars, there is a unique v1. Sorry, I meant left kernel. Doesn't matter. So there is a unique v1 such that if I take phi of u1, comma v1, and leave the third as an indeterminate, I get the 0 vector. Right? So this is just linear algebra. And Now I can ask the same question about V1, right? Except that the sport now happens in the second dimension. So I take the inner product of V1 and phi, and by design, V1 has corank at least 1. And this is typical, because for it to have corank 2, it's a fewer dimensional constraint. So unless we are unlucky by a probability 1 over q, V1 is still going to have corank exactly 1. So I keep playing the game. I can go to W1, wherein I take the unique projective point on the right kernel, and the fun never stops. I can go back to U2, right? And at each step, the only reason to stop is if instead of a corank precisely 1 projective point, I get corank 2. And I'm hoping that doesn't happen too often. If the field size is big enough, it doesn't happen. Right, so to what end am I doing this iteration? And I'm going to do it n times, right? And once I stop, I'm going to collect all the vectors that I see. And I'm going to hope that each of these 3 sets of vectors is linearly independent. Again, there's a fair chance of that happening. So these 2 are heuristics. We don't know how to prove it. And these are the only heuristics, essentially. So if I were super lucky and none of these were singular, so they're all invertible, I can just write these sets of n vectors as square matrices, right? So starting from U, I've determined 3 square matrices. So all I do is I act on phi by that triple, and I get my invariant. I have to stress that there's a lot of intricacies that I'm hiding. In particular, at each step, I'm doing things projectively. So there is a cost I'm paying by taking a choice of the representative. So in some sense, to claim that the invariant is a tensor and not an isomorphism class of a tensor, I have to make those choices very carefully. Essentially, what happens is that I have to quotient out by the center, which happens to be a product of diagonal groups, and all this can be done. So the short answer is, if I take phi and a corank 1 u, and I do this procedure, and unless I'm unlucky, I get a unique tensor, which is bracket phi comma u, right? The moment I have this construction, I can look for collisions. So the algorithm is fairly straightforward now. I have 2 inputs, phi and psi, and I'm going to sample 2 sets of corank 1 points and compute the corresponding invariance and look for a collision. And if there's a collision, then these 2 isomorphisms composed the right way is going to give me an isomorphism from Pierre and Lot. And the crucial observation here is that the number of corank 1 points in both cases is roughly q to the n minus 2. This is, again, simple dimension arguments. There are more precise estimates. And thanks to birthday paradox, it suffices to sample each set, which is square root of that size. So I get q to the n minus 2 over 2. And that's the algorithm. And all this pain was to get this 1 over 2 in the exponent. And there is some polynomial factors. So asymptotically, MEDS's bit security needs to be sort of cut in half. But for actual parameters instantiated in the NIST submissions, the polynomial factors are also important. So it's not precisely cut in half, but a significant number of the bits are lost. But I have to stress that this just shows that you can do birthday attacks. And there is no cause to panic. It still looks like an incredibly tough problem, and a whole slew of complexity problems reduced to tensor isomorphism. And we propose a simple fix, which is to increase the bit length of the prime or the prime power, which is the field size. You double it, and it should be fine. And this affects the signature size, so that's not great, but it doesn't really affect the runtime. Okay? So it's a cause for caution, not panic. So I'm not claiming any break of anything. It's just work to get a half in the exponent. Okay, what can we say about Altec? Not as much as in MEDS. So the reason is, one thing I hid in the MEDS discussion is that even going to corank 1 and doing this, this weird iteration gave us invariants that are sufficiently distinguishing. So if I map everything to, like, say, 0, that is a perfectly good invariant, but that is useless for actually finding useful collisions, right? Like, so ALTEC, we don't know how to do it with corank 1 points. So we have to resort to much higher coranks, say R. And in this case, if I take phi, which is the tensor, and take inner product with U, as before, I get a matrix, and this matrix has a kernel of dimension precisely R, right? So the invariant is going to be the restriction of the tensor, wherein the first dimension, it's restricted to the kernel of this kernel U. And the other two dimensions are as before. But the trouble is, now the invariant is not really a tensor, but the isomorphism class of a tensor modulo this group action where on the first dimension you have the symmetries of the kernel, and in the second and third dimensions it was as before. So in some sense, if we get collisions here, we can't really tell if we have a collision because we have to solve another isomorphism problem, which is similar to the one we started with. It would be nice to do recursion, but I don't know how to do it. But the saving grace is that there is more here. So if I start with phi and sample a corank RU, and if I start with psi and sample some corank RU prime, then this U and U prime actually acts as partial information, wherein you can feed that to certain Grosvenor basis solvers to augment the multivariate system that characterizes the actual problem. And curiously, at least heuristically, this tests isomorphism in polynomial time, heuristic polynomial time. And so this is good enough, almost, to do the collisions. But in truth, it is not quite good enough, because to actually do like a birthday attack, just testing isomorphisms is not enough. So this is not entirely true. I'm like hiding a lot of things under the rug. So we really need canonical forms. So for instance, if you look at Babai's graph isomorphism problem, like an algorithm for isomorphism comes out, and like 6 months later, there's a canonical form algorithm. So if there is a canonical form algorithm, everything goes through. But in the quantum algorithms case, we have a trick wherein we can circumvent the need for canonical forms, and everything works there. Okay? I'm going to end very soon. So the last thing I wanted to say is that all these methods, they fit nicely into very well-known quantum algorithms that do collision finding faster than classical ones. But all of them come with the caveat that you might need like exponential size quantum circuits in some cases. So it's fun to know, but perhaps too pessimistic to base your security on these. But I would like to end with an open problem, which is that if I look at tensor isomorphism problem, it's fairly trivial to phrase them as a hidden subgroup problem over general linear groups. And these are notoriously hard to solve on quantum computers, because the best known methods, which are extensions of Shor's algorithm using representation theory, you can do it statistically, but when you actually try to do it computationally, so general linear groups have lots of irreducible representations, which are of high dimension. So this is one of the hardest hidden subgroup problems, and harder than symmetric group, even before Babai's algorithms. And so my curiosity is there a reduction that goes the other way, wherein you can reduce some generic hidden subgroup problem over general linear groups to a tensor isomorphism problem? It's plausible because tensors are usually defined universally, right? Like, so they should capture any linearity. And I'll end with that. I don't know the answer, and happy to take questions.
Thank you, Anand. We have time for 1 or 2 quick questions.
Thanks for the very nice talk. There is a difference between 2-dimensional tensors or matrices and 3-dimensional tensors. What happens if I go to higher dimensional tensors, the same trick, with finding a collision and co-rank 1 points will apply?
So the first thing, in terms of complexity theory, all those problems reduce to three-dimensional tensors. But of course, the reduction in some cases is polynomial in the input sizes. So it's not quite satisfactory to answer cryptography questions. And in some cases, it's constant, but still the constant could be big. So theoretically, we could just phrase everything as a three-dimensional problem and solve it. But since we are like pecking at small constants in the exponent, I don't think it helps directly. But there's a chance to take your idea directly and apply it to higher dimensions, and it might work. I'm not sure, but there's a chance.
Right, if there are no further questions, let's thank Anand again. Can we bring up the slides for the speaker? So the next talk will be on asymptotics and improvements of sieving for codes, and will be given by Simona Jatinsky. Please, Simona.
Thank you very much. So this talk is based on the work asymptotics and improvements of sieving for codes, as Andre already introduced, and it's also done in collaboration with Andre here, and Andre Esser, Yelena Kirshanova in the audience, and Leo Duca. And I would like to start with the motivation for this work, which comes from the lattice-based world, in which sieving is a very well-known technique, state-of-the-art for attacking lattice-based problems, decoding problems in the lattice-based cryptography. And a natural question occurs, actually, how well these techniques perform in the code sieving setting, in the code-based setting, in which you also have decoding problems that are of quite similar flavor. And there were different attempts to actually already try to adapt these sieving techniques to code-based setting. Some of them more successful, some of them less successful. And so basically our goal was to make them successful, and in particular to adapt sieving techniques to the code-based setting, and more precisely to make them competitive with the state-of-the-art algorithm, at least in the asymptotic sense. So I would now like to start with the sieving for codes. And before actually introducing the technique, I would like to recall the decoding problem that you are probably all familiar with, given that you are in this room. So it is defined as follows. So given some nk binary linear code C, where n is the code length and the k is code dimension, as well as the weight w, which is some integer value, you're asked to find a code word of weight w. And so in the code-based case, we are asked actually to find a code word of Hamming weight w, while in the lattice-based case, its equivalent would be in the Euclidean space. And now I can actually come back to the code-based world, in which the ISD algorithms are actually the best-known generic attacks for attacking this problem. And I would also like to mention here that there are some different like algorithms that work for specific regimes, but here we are actually interested mostly in this generic case that works for all parameters. And this algorithm was originally introduced by Pronsch in his work in '62, and further improved by so many people that it cannot even fit here, like the list of all the improvements. But we are primarily interested in the performing of the sieving ISD algorithms that were obtained by putting sieving as a subroutine of the ISD. That was introduced in the paper by Johansson and Nguyen from the last year. So the high-level idea, so very high-level idea of this approach is actually to observe like ISD algorithm as a kind of a black box that produces a sub-instance of this problem, and ask sieving oracle A to provide many solutions to this sub-instance. And so our idea was actually to generalize this approach a bit more by introducing another layer, which corresponds to the near neighbor search oracle that is presented in the orange box here. And what we know is that the running time of the ISD algorithms can be seen as the running time of this like sieving oracle that was in the second layer of this algorithm. And it also depends on the probability P1 that in the information set decoding framework, you already guessed a part of the solution correctly. as well as that the oracle that is invoked by the information set decoding actually gives a solution to the original problem. So the runtime and the memory of the sieving part, or actually of the second layer, is dominated by the running time of the oracle for near neighbor search, here denoted by B. And so the focus of our work was basically what is the runtime of this, to improve the runtime of this oracle, or the techniques for using the near neighbor search. So let us now focus on the near neighbor search. This type of techniques was already introduced even in the context of information set decoding without the sieving, in the work by May, Ozerov, May, in the thesis of Kevin Carrier. And in the lattice-based world, it was actually quite successfully combined with sieving techniques, and in particular locally sensitive filtering that was introduced in the paper by Becker et al. But before I start with describing how these techniques combine well together, I would start with certain definitions that will be relevant through the rest of this talk, where we have a sphere of radius p, which is basically the set of all the vectors that are of weight p. We call the near neighbors the vectors x and y that are on the sphere of radius p that are exactly a distance p. As you can see it from here from the notation, it basically, so we use plus as the bitwise XOR, which basically means you have a distance p in the Hamming space. Equivalently, we can also see that if the two vectors are already of weight p, so to be at the distance p, it basically means that they overlap in exactly p over 2 positions, which will be something that we'll use through the rest of this talk. So now I can actually introduce the near neighbor search problem, where we are given an input list, which is a subset of a sphere of radius p and the target weight p. And we are asked to find all pairs that are in this list that are at distance p. Or equivalently, we can say that they are overlapping exactly p over 2 positions. And what we know about this problem is that, if brute search over this problem would be would run in time that is like a square of the list size. Here the notation should be on the list size. And the question now is, can we improve this? So can we do any better than brute force search? And the high level idea, given already in the locality sensitive filtering, in the paper on the locality sensitive filtering, introduced the approach in which you are basically localize this search in the area, in a small area over the sphere, where you assume that the vectors are already quite close to each other. And in particular, so in the Hamming weight case, we will define it as the overlap alpha. So if the x and y overlap with c in this integer parameter alpha, we will assume they are close in space. In the Euclidean metric, you can see that as vectors that have very small angle between them and c. And this is how we will actually approach this problem. So we will start from the sphere of radius p with some certain number of points that are sampled uniformly at random. And then we'll also take certain centers. So in this case, we'll choose the set of centers that are C1, C2, C3 on some smaller sphere, and as well as a parameter alpha, which will enable us to perform the bucketing phase, in which we'll basically split the space into these regions that corresponds to the vectors that are close to each other. And in the bucketing phase, basically for each element in X, in the list L, we will check if it overlaps with the corresponding center in alpha positions, and if it does, we will put it into bucket that corresponds to this bucket center. In the checking phase, we will then perform the search for the near neighbors only within the buckets. And to be a bit more precise on this algorithm, so we start with the input that is weight p, the input list L that is a subset of vectors on the sphere of radius p, the set of centers CF, and the bucketing parameter alpha. And we output list L prime that contains pairs x and y in this list that are near neighbors. No, it was not. So we start with performing the bucketing phase that I already mentioned, in which we go through all the elements within the list and perform the find valid center subroutine that actually checks for all of these elements and all the centers where they like overlap in the alpha positions. And for all this C in which X overlaps in alpha positions, it puts it in the corresponding bucket. So we then continue with the checking phase, in which for each bucket or equivalently for each center in the set of centers, we check all the pairs and we add them to the output list if they are near neighbors. And as you can see here, like basically the cost of this will primarily depend on the cost of the find valid center subroutine that we will try to optimize, as well as on the number of the buckets and the size of the buckets in which we are performing the search. More precisely, the runtime will be given as the length of the list multiplied by the time for finding the valid centers, and the cost of the bucketing phase will depend on the number of the buckets as well as on their size. That is basically corresponds to the cost of searching through the buckets. The memory we will also try to address will depend on the input list size, of course, as well on the number of the valid centers, and it is basically only the memory that is necessary for the bucketing phase of the algorithm. So our initial goal was actually to balance the trade-off between the bucketing and the cost of bucketing and the checking part, and like once we actually obtain the algorithms that are doing that, we also try to improve the time memory trade-offs. So I would now start with the approach from the paper of Guo, Johansson, and Nguyen. Sorry for the mispronouncing the certain names if it happened. And so the basic idea and the starting point was that the observation that for any x and y that are on the sphere of radius p, and that satisfy that there are actually overlapping p/2 positions or that there are near neighbors, there exists a unique center C, such that x and C and y and C overlap in exactly p/2 positions. And I need to mention here that this is not initially seen as a locality-sensitive filtering approach as in our case. Nevertheless, if you recall the parameter from the previous, if you recall the algorithm from the previous slides, and you take this CF as the input, where the input set is actually all the points on the sphere of radius p/2, and you take the bucketing parameter alpha to be, again, p/2, you will actually recover their approach. And in that case, what you obtain is the buckets that contain no false positives and no false negatives. So all the solutions are detected. All solutions are detected exactly once. And it turns out to be a bit unnecessarily restrictive. And already in some previous paper, it was shown that it's possible if we relax these parameters that we can obtain some improvements. And our idea was actually to increase the size of the buckets and reduce the number of the buckets efficiently, so to obtain a bit better trade-off. And in particular, so what we choose was the set of the centers CF, that are some points on the sphere of radius alpha, where alpha is a bit smaller than p/2 now, which give us a bit bigger buckets. But in the same time, we also require that these centers also belong to the code CH, which is another binary linear code completely independent on the original instance of the problem. It's just like a technique for solving it. And in that case, what we managed to obtain is actually a routine that is like a subroutine for find valid centers that is quite efficient, because this choosing R properly, we can actually perform this quite efficiently. Next step in this direction was actually introducing the random product codes that should improve even more the efficiency of the find valid center subroutine. And in particular now, instead of choosing the one big random code, we are choosing basically a Cartesian product of the small codes, CHI in this case. And so in order to guarantee that these codes still have the behavior as the random code from the previous approach, we also need to guarantee that T is small enough, and in the same time, T needs to be high enough so that we actually obtain some improvements. And in our paper, you can see what is actually the property to choose. And final improvements came from the memory optimal versions of the hash-based and RPC approach, in which we basically interleave the bucketing and the checking phase. So instead of performing the bucketing on all the buckets, we choose like d fraction of them, and then repeat the algorithm d times. And what this, of course, introduces some like overhead in the runtime. Nevertheless, if we choose the parameter d properly, this overhead is not too high. And on the other hand, like since this like memory is only used in the bucketing phase, we can reuse the same memory in each iteration. So now, I would like to present the numerical results that give you maybe a bit better intuition what are the improvements we obtained. So as I already mentioned, we were primarily interested in the asymptotic runtime, and actually more precisely in the exponents of the asymptotic runtime. And for each, which are the function of the code rate, that is basically the proportion between the code dimension and the code length. And for each R, we actually also determined what is the value of W that corresponds to the Gilbert-Forshaw bound, which give us a unique decoding regime in which the problem is considered to be the hardest. And here, here are the numerical results that we obtained for different algorithms. So in particular, like Prange algorithm is taken as the baseline, like it was the first approach. After that, so you can see that already through the approach from Guo et al., you can obtain some improvements in the asymptotic running time. BGMM is the best, so the algorithm that works the best in practice. And you can see that our hash and RPC memory optimal versions are actually even slightly better than it in the asymptotic running time. We are, nevertheless, we are still not reaching the both May approach. That is the best asymptotic, that is the best in the asymptotic sense, but still yields a very high overhead in the practical setting. And here, here are the time memory trade-offs for different variants of our algorithms, where you can see that actually the memory optimal versions, both of the hash and RPC, actually gives you a lot better trade-off. And in this particular case, also RPC memory optimal is actually the best we could hope for right now. So to sum up, so what we did, we introduced the sieving-based algorithms whose asymptotic running time is very comparable to the, actually quite close to those of the state-of-the-art, in particular the BGMM. And apart from that, from more theoretical point of view, we provided a new alignment of the code-based crypto and the lattice-based crypto that is considered to be quite relevant given the problems are quite similar in flavor. So the question remains how practical this is. And yeah, this is the question that is still open. And for more details, you can consult our ePrint version of the paper or GitHub repository in which you have like the numerical analysis of the algorithms as well as some experiments on the heuristics. So thank you very much for your attention.
Yes, we have time for some questions. Just a quick announcement for the next speaker. Charles, could you just go to the technical team in the back to get prepared? Thank you.
So if I understand correctly, your algorithm is a heuristic which doesn't always succeed, but succeeds with high probability. Is this the case, or?
So thank you very much for your question. So in fact, like this, the sieving part of the algorithm relies on the heuristics, which is like a common setting both in the lattice-based and code-based cryptography. And so nevertheless, this heuristics was validated through both the experiments, like in the lattice and the code-based setting. The part that I presented, that was mostly on the near neighbor search, does not depend on the heuristics. So it succeeds. So
Okay,
yeah,
thanks.
Thank you.
Hi, thank you. I was wondering, do you see any obstacles to implementing or to adding to this picture tuple sieving in the code base?
No, so I mean, to be fair, we didn't try it, but I don't see why like there should be any like theoretical or like non-theoretical obstacle to do that, like a case sieving, or I guess I assume you're asking about. No, I don't think there would be any issue, and it might even yield some mild improvements. So. Yeah, I guess it would be an option, yes. Thank you.
Yeah, thank you very much. I think it's very nice. So when you compare to my Osirov, you didn't do that. Does it improve or is it similar?
So I just didn't put it there. Yeah. It improves slightly, I would say, simply.
Because it seems to be way more practical, right?
Yeah, so it depends, like if you observe the running time, so I cannot like tell you for sure, but in the time memory trade-offs, I think it improves, yeah, already in this picture. So I wanted to just give the comparison of our paper, but even in the time memory trade-off, you can actually see the improvement.
Right, if there are no further questions, let's thank Simona again. So the next talk will be on reduction from sparse LPN to LPN, dual attack 3.0, and it will be given by Charles Meyer-Hilfiger. Please, Charles.
Thank you, Andre. So this is a joint work with Kevin Carrier, Thomas Debrial-Lazare, and Jean-Pierre Tillich. So today I'm going to talk about dual attacks in codes and lattices. So first of all, I'm going to talk about codes. So there is a lot of code-based primitives, notably in the NIST competition. And all of these primitives the security rely on the hardness of the decoding problem. So what is the decoding problem? Is I give you a binary linear code of length n and dimension k, so just a linear subspace of dimension k of f2 to the n, and I give you a noisy code word of this binary code. That is a code word plus an error vector e of small Hamming weights. And I ask you to find the error vector e. So basically what I'm going to present is a new decoding algorithm. So the state of the art right now, not the state of the art, but the decoding problem here I've plotted is a hard problem, exponentially hard problem in the length of the code. And I've plotted here the complexity of some decoding algorithm, so primal attacks, depending on the rate of the code, so the dimension over the length. So in blue here you have a Prunge algorithm, which is the first non-trivial decoding algorithm. And in green here, you have a Bot-and-May algorithm, which is the state of the art. Okay. And so you see here that in 60 years, the low-weight regime have very little improvement. Now, recently, in 2022, with our co-authors, we introduced Dual Attack 2.0. And in fact, we reduced the decoding problem into an LPN problem. So what is the LPN problem? Is you have a secret, S, and I give you many samples, which are of the form S dot product some A, plus a noise term, which will be biased towards 0. Okay? So I give you many samples, and I ask you to find S. And so what it did when we did this reduction, we get an algorithm which beats a previous algorithm for rather small rates. So we have a big improvement for small rates. And now, in this work, what we will notice is that our first reduction, when we reduced to LPN in 2.0, the LPN problem we reduced to was in fact sparse, which means that the secret is a small Hamming weight. So in this work, we will use the sparseness of the secret to reduce to a plain LPN, but of smaller dimension. And I have plotted in black here the complexity, the curve we obtain with our new algorithm. And we beat all of the previous decoding algorithm for rates smaller than 0.42. Just to tell here, this curve, all these curves are plotted at the hardest decoding distance. Okay, so now I'm going to present the state of the art, which are dual attacks 2.0. In dual attacks, of course. So the setting for dual attacks is the dual of the code, which is just the word of the space that are orthogonal to all of the code words. And what you can do, why it's useful, is that when you compute a dual vector, H, and you are given the noisy code word you're trying to decode, C plus E, you can compute the dot product of this noisy code word and H. And because H is a dual vector, C and H cancels out, and you only have left a linear combination of the error. The question now is how to exploit it. So this was the goal of Dual Attack 2.0. So the goal is to reduce this inner product into LPN sample. So what we do is we will split the support into two complementary parts, P and N, and we are going to try to recover the error on the part P. And so what we can see is that if we compute a dual vector that is now of small Hamming weight W on the part N, okay, and we split the previous dot products that we computed, E dot product H, into the part on P and the part on H, you can see that now you have in fact a LPN sample, where the secret is given by E on the part P, and the noise term will be given by E on the part N dot product H on the part N. So why is this LPN problem? It's because this noise term on the right is actually biased towards 0. Because one, the error E is an error vector from the decoding problem, so it's of small Hamming weights, and H has been computed of weight W, which is small. So you have a dot product of two sparse vectors, you have something that is biased towards 0. So our algorithm will compute n dual vectors to get n LPN samples as follow. So the dimension here is f2 to the size of p, okay, of the LPN problem. Okay. So now one of the key questions is what is the hardness of this LPN problem? And in fact, it's a hard LPN problem. So how do we estimate it? Is that we have the noise term, I recall to you En dot product Hn, and the key component here is the bias of this quantity. So it's just defined as the probability over the samples that En dot product Hn is equal to 0 minus the probability that En dot product Hn is equal to 1. So basically, the more this bias is high, the easier the problem will be. And so what is important is that this bias can be computed theoretically only using the weight of the vector, which are known quantities, okay? And this is exponentially small, this bias. So this is what will make our algorithm exponentially difficult. So a lower bound, there is a sample lower bound that can give you the required number of samples in function of the bias, which would be sufficient to be able to recover the secret vector EP. It's just to give an intuition. Okay, so how do we solve this LPN problem? Okay, we have our LPN samples, we have a secret S. How do we solve it? The key function here is called a score function. Okay, so it takes as input basically a vector x, and it will tell us how likely it is that x is the solution. Okay, so the higher this score function, the higher it is likely that x is the solution, so the secret. So basically, the score function is just the bias of your LPN sample here minus a dot product x. Okay, so you can see that when x is equal to s, you have this two extramal term cancelling out, and you only have left the bias of E, and you expect it that, so the bias of E is way higher than the bias related to all of the other x's. So if x is not the solution, you will expect that this bias will be smaller. So what you do, in fact, you compute this score function and you take the maximum. Roughly, you take the maximum. And to do that, to speed up computation a lot, exponentially, in fact, you use FFT over F2 to the P to compute all values of the score function, okay, on the space F2 to the P, and then you take the maximum. Okay, so it's still exponential, but you gain something from doing that from naive enumeration. Okay. Okay, but now there is a key remark here, is that basically, okay, we did our FFT to solve the LPN problem, but we never use the fact that the secret, which is given by the error vector restrained on P, is sparse. Okay, we computed F for all x's and we didn't use the fact that S was sparse. So this is now the goal of our algorithm, dual attack 3.0, is to use the sparseness of the secret to speed up our algorithm. So what is the approach is to say, okay, we will just transform our LPN samples, so here you have the starting LPN samples, to some other related LPN samples, okay, here, but of lower dimension, okay? So it will come, of course, at the cost of an increased noise, but you will transform this problem into another problem where the new secret, S prime here, will be somewhat related to the older secret S, okay? So more technically, what do? Is we will approximate A, so the sample, into a lower dimension subspace. Okay. So basically, how do we do that? We take a linear code, okay, COX, which lives in the ambient space, okay, and we will just decode our sample A into this linear code. So basically, we can write A as a code word COX plus an error vector, which will be of small Hamming weight, because it comes from the decoding. And what you can see is that if you take your LPN sample here, you can directly rewrite it using the previous expression of A. So you split A, and you have S, the secret dot product COX, plus a new noise term, okay? This new noise term is actually just the sum of the old noise, E, plus S dot product EOX. And you can notice that because S is a sparse vector, okay, so we said that the secret was sparse, and EOX is a sparse vector, this dot product will be biased towards 0. So in fact, we have increased the noise here, but we didn't increase it too much because we added a dot product of sparse vectors. And the interesting thing you can notice is that now your LPN sample is the secret dot product, something that lives in a lower dimension subset. So how can you use it? You can just notice the fact that the code word COX can be written as components of the basis generating the auxiliary code here. And so you have COX equal M times G, and you can just revert the position of the matrix to get this quantity here. And the important thing is that this quantity, MOX, and this new quantity on the right, lives in a space that is a smaller dimension. So it's in F2 to the dimension of the auxiliary code. Okay? So this is what will give you your advantage. So of course, your new secret is just a linear combination of the old secrets, but you have gained. Okay. So now we will solve this new LPN problem as before. We will do a FFT to solve the LPN problem. So we will define the score function, which is as before the previous score function. And now there is a quick key question for the complexity analysis is, okay, I've told you that when the score function is high, we will say, okay, this is our secret vector S. But the question is, how many x's will be mistaken for the solution? So how many x's will have a high bias, okay? So this quantity. So previously, what were done is we need to study actually the distribution of F to understand, okay, what does it look like? And if we do a bit of history about dual attack, first, to understand the behavior of this core function, independence assumptions were used, okay? And basically, in dual attack 2.0, we noticed some experimental differences between the behavior of the score function and what would be given by this independent assumption. But we conjectured that it was not so bad. In 2023, with Jean-Pierre, we showed that it was not working at all, this independence assumption, and we proposed a new model to predict accurately the behavior of this score function. Okay. And so here, going back to dual attack 3.0, so our new attack, we can see I've plotted here the experimental distribution of the score function and what we would expect if the independence assumption were true. Okay, so basically you see that the red curve, the red experimental curve doesn't match at all with the independence assumption. No problem here, it is expected that it does not work. Okay. So what we do here is we we generalize the work of our work to analyze dual attack, or new dual attack. So basically, we are able to devise a new theoretical model, okay, to predict the behavior of this the distribution of the score function. So basically, I've plotted in blue here the new theoretical model we have to predict dual attack 3.0. Okay. So how do we get this model? So it matches perfectly with the experimental curve. So how do we get this model? We do as the previous work, we devise a dual formula for the score function. This dual formula make intervene the number of code words in some code, okay, of a certain weight, and make intervene Kraft-Chuk polynomial of degree W. So basically, to get this dual formula, what do? We just we use the Poisson summation formula on the score function to get a dual formula, and we use the fact that the Fourier transform of the indicator variable of weight W is in fact the Kraft-Chuk polynomial of order of degree W. So this, of course, this indicator variable comes because we consider dual vectors of weight W. And then, okay, we have this dual formula. We model the number of code words of weight E in some code by a Poisson variable, and we are able to get a model for the distribution of the score function. Okay, so lastly, I'm going to present a prediction for the score function in lattices dual attacks. So I recall to you that Duca and Poole in 2023 showed that the independence assumptions are invalid in lattice dual attacks. So basically, in blue, you have the same setting in dual attacks in lattices. You have a score function that you expect will be high on the secret, etc. And usually they use independence assumption. And Duca and Poole showed that here they showed that the independence assumption could not hold. So in blue full line, you have the experimental result of the distribution, and in dotted blue, you have what should have been given by the independence assumption, what you should have by the independence assumption. Okay, so this is a problem. So now the question is, how can we predict this curve? So what we do is we adapt our previous work, but we shift it to analyze dual attacks in lattices. And what we do, we devise a new model which perfectly match the experimental curve which was observed by Duca and Poole in 2023. So this is the first step actually to analyze correctly the dual attacks in lattices. And what we do is we devise, as before, a dual formula for the score function. Now it makes intervene lattice points of a certain length and Bessel function. And why Bessel function come here is because to get this dual formula, we use the Poisson formula, plus we use the fact that the Fourier transform of vectors of length smaller than W is a Bessel function. Okay, so it's the equivalent of Krafft-Schuck polynomial. Okay. So now, to conclude, we have given a new algorithm which beats the state of the art for height smaller than 0.42. Our analysis does not rely at all on independence assumption, and we are able to predict the score function of lattice-based dual attacks. Thank you very much.
Thank you very much, Charles. Do we have questions for Charles?
Can you go back to page...
Oh, fuck.
Can we have the slides of Charles back on? Thank you.
Page 16, I believe.
16? Okay. Tick, tick, tick. Yes, here.
Yes. So I'm struck by the shape of your theoretical graph. It should be smooth in some way. The non-smoothness could happen for small values of t, but these t are very large.
You mean, where do you mean?
Why does it go up?
Because, okay, when you see, okay, there is a very clear indication for that. Actually, you have this sum of code words of weight, some weight I in D times Krafft-Schuck polynomial. And actually, what you see in these high values of the curve is rare event, okay? So when the code here, the code D, will have a low weight code word. So in fact, the little bumps here comes from when you have a code word of weight small, and then another very small code word.
So it's misleading to think about the right-hand side as corresponding to large numbers. You say actually the right-hand side of the graph corresponds to very low weight code words.
Exactly. It's when these codes here have very low weight code words. Exactly.
Because right now the numbers look huge.
Yeah. But usually, because actually it's because for each X you will have a different code word, different code associated to it. So
now I understand. Thanks.
Thank you for the question.
Thanks for the talk. Can you go to slides 19, please?
19.
Yeah.
Okay, yes.
How do you compute NI of lambda?
Sorry?
How do you compute
the
number of lattice points?
Actually, it would be like, we devise it from we have the Poisson model for lattice points of length lower than I. And you can model the number of lattice points of length lower than I by a Poisson variable also, and from that you can devise Roger.
It's a go. Okay.
And then from that you can. But actually, we don't use this formula because it's a bit what. So I don't. Okay, in 2 seconds, what we do is in fact we just have our approximation. We just need actually the length of the shortest vector. So we just approximate it by the exponential distribution, but it's so we don't. But if we wanted to, to have a model for all the code words, we would use the Poisson formula.
Okay. Thank you.
So at the moment, you assume that your weight is linear in n, right? And then you compare all the algorithms.
Yes, exactly. The weight.
What happens if you are even sparser? Let's say you are in a regime where the weight is n over log n, like for Lebanese, so square root of n. Do you then collapse back to French's algorithm or French complexity?
Okay. So
or is there a chance that you can actually improve?
Actually, so this is a work in. We are looking at it. But what I can say is exactly when the weight is sublinear, you begin to converge to French algorithm like the primal attacks actually. But what is interesting is, but this is
maybe second order term you can still improve, right? So first order term you.
This is what this is the question we are having right now. Yes.
Yeah, that's nice. Yeah. Okay. Yeah, perfect.
Okay, I also have one last question.
Yeah.
So in fact, you used this reduction to go from a sparse LPN instance to a regular LPN instance with reduced dimension. Did you investigate somehow the optimality of this reduction? Like, is the gain in the dimension as high as the entropy loss that you have due to the secret known that it's sparse, or is there a hope to maybe target instead the Fourier transform for sparse vectors or something and improve this instead of?
Okay, I'm not sure I will be able to give a full answer to that. But what I can tell you is that when you look at the parameters, basically, blah blah blah. Where is it? Here. You know what? Okay. When you look at the parameters, you have the weight of the secret here, and you have the auxiliary code. What we have is that there is. It's just an intuition to say why it looks optimal. Given our parameters, there is a unique, when you look at a syndrome like that, there is not a unique, but there are many syndromes of a given weight, which will be sorry, I'm trying to, okay. When you look at the parameters, the reduction looks tight because your secret can be associated to many vectors. So when you solve this problem, there will be many vectors of good Hamming weight, which will be, with this syndrome. I'm not sure I'm clear.
Okay, otherwise we can maybe...
I'm sorry, I'm not clear. I understand.
I have a feeling for it, but I'm not 100% sure. But let's maybe continue the discussion offline. And then this concludes the session. Let's please thank all the speakers again.